Hello class, and welcome to the second lecture from the first lecture of week 8, that should be, but the second lecture for the material section on wood and wood products. So if you remember, we talked about what we would be learning in this section. We would be looking at key properties of wood. Now, yesterday for me when I recorded the lecture, but the last lecture for you, you looked at basically key terminology of wood. You looked at key properties, namely the moisture content, and how factors such as the type of wood, the time of season, and also whether it's a hardwood or softwood or heartwood or sapwood, how they influence the moisture content. And basically we also talked a little bit about how variability in moisture content that can wear out the wood because it basically is always swelling and shrinking. We also talked about how sometimes we want to have a high moisture content because that means we can increase the high moisture content, bend the wood into the shape we want, and then lower the moisture content, and because it's plastic deformation it will stay in the new shape. So we also talked a little bit about how moisture content influences the modulus of elasticity and how that can be used for malleability, basically bending wood into new shapes. Now we're going to be talking about a couple of new properties with wood today. We're going to be talking specifically about the strength of wood, and then we're going to talk a little bit more about durability. So let's jump right into strength. Now there's a couple of things you need to know. Strength, as we have discussed before, it can be have different values, whether the load is in tensile, shear, or flexural or compressive. Normally we just look at shear and compression and tension for the most part. But what you need to know is that the grains of the wood, basically the fibers, those wood cells, the strength will be considerably more if the loading is basically parallel with those grains. So in terms of tensile strength, if you're trying to pull those grains out of one another, and so they're basically parallel, then the strength will be 10 to 20 times greater than if you were trying to pull the grains apart and the loading was perpendicular. Does that make sense? If that's not clear, maybe I'll try to show this to you on the whiteboard when we have our Zoom tutorial, or phone me up now and I can try and explain this to you over the phone. Now remember, the shear strength of wood is normally about 10 to 15% of the tensile strength, assuming that the strength of the tensile load is in the direction of the grain, parallel to the grain. So wood tends to have very good tensile strength, a bit weaker in shear strength. But the really important thing you need to know as a practical civil engineer and not as a wood scientist or specialist is that wood can lose up to 90% of its tensile strength because of defects such as shakes and cheeks and knots. Knots especially, there's not a lot of strength in those knots. You might as well have a big hole drilled out of the wood there. So remember that when you're looking for wood, make sure there's no knots in it, because that can reduce the strength drastically. So let's look at tensile strength here. We've got a few different options here, few different woods, and remember, generally if the wood is taken from the heartwood, rather than the sapwood, the tensile strength will be a little bit greater. But here we have tensile strength measured parallel to the grain. If it was perpendicular to the grain, then these figures would be maybe 510 megapascals. It would be considerably less. But you can see there's actually quite a variation in tensile strengths there. Look at pine, that's got a megapascal of 40 to 110 for tensile strength. Look at Osage orange, that's quite a rare wood, but that's 190 to 210 megapascals. Now look at this. Generally, the ones in black, those are evergreen trees, those are hardwoods, and the ones in red, softwoods, and those in red, they are deciduous trees, they are hardwoods. Now there's a bit of variation amongst them, but there isn't really a variation between softwoods and hardwoods, are there? You've got stronger and weaker woods in both categories. But you've got to remember that it's the defects in the wood that's what really reduces the tensile strength. The other thing to remember is that moisture content doesn't actually have much effect on tensile strength. It has a little bit more effect on compressive strength, but not a lot. Where we care about moisture content is really how it can affect the durability of the wood, especially if there's variation in the moisture content. That's the important thing. So I don't know if you noticed with the last slide, but there was one particular evergreen tree, a softwood, that had a very high tensile strength, and that was bamboo. That has a tensile strength of, it can go as high as 250 megapascals tensile strength. That is very, very strong in tensile load. The thing you need to remember about bamboo, though, it's very weak in compressive load, very weak, and also it's not very malleable. It has a very low ability of absorbing moisture, and so you can't really bend it into different shapes. You're basically reliant on using bamboo in the shape it comes in, these sort of long cylindrical tubes. So there aren't too many things you can build out of bamboo, but one of the things where it's very useful is for scaffolding. Now, I think here in Kurdistan, for the most part, people are using aluminium scaffolding these days, but in many parts of Asia where bamboo is quite regular, quite available, they will do scaffolding out of bamboo. It's very stiff. It's got very little elasticity. It won't bend and twist in the wind, and the tensile strength is such that actually people can walk across it, and so it's very good flexural loading. And they build absolutely huge buildings using just bamboo that's lashed together. See how it's lashed together with rope? You can't actually use bolts and things with bamboo. I'll get to that, but you can build huge buildings. Look at that. That's a huge high-rise. Those people are probably 70-80 meters off the ground, and all of that scaffolding is bamboo. Now, that's actually quite terrifying, just the safety standards there, no safety rails or anything. I'm not advocating that we ever build buildings using bamboo scaffolding, don't get me wrong, but nonetheless you do see the capacity of the material, just the tensile strength there. And this one is absolutely incredible. I saw this in New York. This is about 40 stories high. This is around 50 meters higher than the tallest building in Erbil, and they were building it using bamboo scaffolding. I find that absolutely terrifying and impressive at the same time, in equal measure. So that gives you an idea of what bamboo can do. Of course, all of the bamboo, it needs to be lashed together with rope. You can't drill a hole in the bamboo and put a bolt through it. Why is that? Well, yeah, those are the lashings there. So there it's actually got fiber lashing to hold it all together. You can't bolt it together. And the reason for that is that if you put a bolt through the bamboo, suddenly you're going to actually have a shear load coming off the bolt, and bamboo is much weaker in shear load. You don't need to know that, but if you're curious about that, ask me in the Zoom tutorial and I can show what I mean by that in on the whiteboard. Now let's look at compressive strength. Now we've looked at tensile strength, but compressive strength, it's often a little bit lower than tensile strength. It's considerably lower for something like bamboo. Bamboo has very poor compressive strength, but for the others, it's usually a little bit lower than tensile strength. Not always. Sometimes some woods actually have better compressive strength than tensile strength. So walnut is an example of that. But generally, it's higher. It's a little bit lower than tensile strength. Now, just like tensile strength, it is stronger if the compressive load is parallel with the wood fibers, with the grain, than if it is perpendicular. But it doesn't reduce the strength quite as much. So remember, with tensile strength, if you went perpendicular rather than parallel, you would only get maybe 5% of the strength available. But here with compressive strength, you're going to get around 50 to 70% strength if you go perpendicular rather than parallel. So it's still quite a significant reduction, and you've got to pay attention to the direction of the grains, but it's not as critical as if it was tensile. Now, one thing that is quite impressive with compressive strength is that with tensile strength, the moisture content didn't really have any influence on the strength. But with compressive strength, generally the lower the moisture content, the higher the strength. Also, with tensile strength, there wasn't really any difference between hardwoods and softwoods. But here we can find that hardwoods are generally stronger with ultimate compressive strength than softwoods. So you can see there, look, you've got oak, walnut and poplar. Those are hardwoods, and you can see that their compressive strengths tend to be a little bit higher than the softwoods. And these are general rules. You can see there's actually quite a lot of overlap. And remember, defects such as cheeks and shakes and knots, they can reduce the compressive strength too, albeit not as much as in the tensile load. Now, these strengths may seem quite impressive, but what you need to know is that if the piece of wood you're using is very long and skinny, you are probably never going to meet this level of compressive strength. The ultimate compressive strength is often not met because of something called buckling. You can get to this strength if you've just got a small block of wood, but if it is a long pole of wood, you're not going to get that. And I'll try and explain that in the next slide. So with buckling, that's basically where you're giving something a compressive load, and if the material is very long and skinny, something like a pole, if it has a high modulus of elasticity, like timber does, it's actually going to begin to flex. And it's not going to flex in all directions the same. It's going to flex in one direction. So it will start to bend like a banana. Now, when it starts bending like a banana, what you basically have flexural loading to a degree. On the outside of that timber, you're going to be having tensile loading, and on the inside you're going to have compressive loading. And so usually the timber will snap long before you get to the compressive load, because you basically have a flexural load going across it, where basically you have tensile loading moving over to compressive loading. I'll try and show that to you on the board in the Zoom tutorial if you want, but it's a little bit further than what you need to know. What you need to understand here is that buckling means it usually fails in compression loading at a much lower loading than the ultimate compressive strength of the material. That's what you need to know. I can try and explain it more in the Zoom tutorial, but this will be covered in more depth when you do strength of materials and structural analysis, those two modules. Those are what I believe are UG2 modules, UG2, UG3 modules. Now, flexural loading, this is very important, isn't it? Because basically, if you have a beam for a floor or a roof, the loading is going to be flexural rather than tensile or compression. So this is where basically you have two loads that are offset from one another. So it's pushing down in the middle of a beam like so. Now, usually, if you look at that beam there that's breaking, and I'm so sorry we can't do this in the laboratory. I promise you we will do this after we complete the module. Normally we would be doing this in the lab, but we can't. What's happening is there is elastic deformation. It will begin to bend, and that means the wood fibers at the bottom are basically being pulled apart. There's tension there, and that's where it's going to fail, because the tension load there is considerably more than the compression load on top, and therefore it's going to basically split, and usually it's going to split as a shake. Remember, the shake is where the grains break apart, because that's where it's weaker. And so if you have round wood where you're basically testing a lumber rather than a square cut timber, it's going to be stronger in flexural strength, because the grains are not going to go to the surface. They are held within in rings, and so it's much harder for these shakes to form. And so it's going to be a lot stronger if it's circular in cross section than if it is square. So that's flexural strength. Again, if that's not clear to you, ask me in the Zoom tutorial. I'm just, if anything's not clear in what I'm saying here, guys, just make a little asterisk, write a small one-word note, and we can go through this in the tutorial. So let's talk about durability here. Remember, we talked about durability. One of the big things was variation in moisture content. That can lead to decay. And basically the first thing is it can lead to swelling and shrinking. So this is a picture from a place where in New Zealand. It's about an hour's drive from where I grew up in New Zealand. But you can see it's a house that is built on stilts, and it goes over the harbour. Now, what's happening here is the tide is going to come in and out. That water level is going to rise maybe 2-3 meters, and those stilts are going to go underwater. Now, you can see that those stilts, they are made from wood, but they've coated them with concrete. Why have they done that? Well, it's not for strength. They didn't need the strength, but the concrete is basically protecting the wood from the wood getting wet. Now you can see this one on the right. That stilt, the concrete has broken away. Maybe it got hit by a boat or something and the concrete broke up. But that wood has been exposed to the sea. And so when the tide comes in, it gets wet and the moisture content goes up. And then the tide goes out and it dries out and the moisture content goes down. And then the tide comes up again and the moisture content goes up. It goes up and down, up and down. That is shrinking and swelling the wood 2 times a day with the tide. And what has happened? Well, you can see there that the wood is slowly decaying and washing away. So that house is going to collapse unless someone replaces that stilt at any time. But that's one thing that can lead to decay. Now, durability is basically how we would measure resistance to decay. So if there isn't variation in moisture content, that gives it more durability. But there's other things that can resist decay too. There's more things that cause decay than just the moisture content going up and down. If there is any kind of moisture content, that actually also means that bacteria, insects, and fungi can live inside the wood, and they will eat the wood, and that will decay the wood. Now, certain woods are more durable than others. So oak, cedar, redwood, they are more durable than pine and aspen, basically because they are denser and there's less room for insects and bacteria and fungi to live in them. It's not a hardwood, softwood divide. All of those woods there are actually softwoods, in case you're wondering. But heartwood is more durable than sapwood. Why is that? Well, it's because heartwood is more dense. It means water can't get in there quite as much, and it means that insects and bacteria and fungi can't get in the wood to the same degree. And so there's more durability with heartwood than with sapwood. So this is insect decay. So what you see there is actually woodworms. This is actually a type of woodworm called a hoo-hoo grub, and they will burrow into the wood, and they've got a very sharp mouth at the front, and they just live off eating wood. And their favorite kinds of wood are basically sapwoods, the soft wood on the outside of the tree, rather than heartwoods. They don't burrow right into the depth of the tree, they just go on the surface because that's where the soft, easy wood is. And so if you have timber made out of sapwood, this is quite a big problem. So be aware of woodworms. They do actually exist here in Kurdistan, they are a problem. And then there's other types of problems, such as termites. Termites are a little bit different in that termites do not eat the wood. And so with a termite, they are basically living in the wood, but they don't eat the wood. They're basically burrowing into the wood to make a place to live. But termites basically eat woodworms and other insects. They don't eat the wood themselves. So they use those big clippers that you see there to basically break the wood and to burrow into the wood. But that means that what they leave behind is a lot of sawdust. And so you can, not a very clear picture there, but That's wood that's been completely destroyed by termites, and you know it's termites because there's all this sawdust in between the wood. They're basically turning your building material into a powder. And this is a big problem in places around the world where they're building houses out of wood. If the wood is not treated well, then you can get termites in the house, and I've seen people lose their homes because of termites. They have $100,000-$200,000 homes completely destroyed in the matter of a year because they had termites eating the floor joists. Big problem. But now this is another picture here. Remember I said that moisture content, you have different kinds of decay. Moisture content can give you insect decay, but it can also, variation in moisture content can give you decay in terms of shrinking and swelling. Now this tree here, this was a tree that I discovered with my best friend. I told you before that my best friend, he grew up on a farm, and I used to spend my school holidays on the farm with him. And one day we were walking along the farm, and we noticed this branch sticking out of the field. And we thought that's interesting, and we started to dig, and we realized it was a branch of a really big karri tree. Now, karri trees are very dense, and because of that, karri trees are not really ever eaten by termites or woodworms or bacteria or fungi. You don't need to worry about decay from animals. But they can decay potentially if there is variation in moisture content. Now, what was this karri tree doing underground? Well, what it was a swamp karri. There are, as I said, karri trees in New Zealand are protected now. You're not allowed to cut them down. They're a protected tree. But what happened around 6,000, 7,000, 8,000 years ago? About 6,000 years ago. Well, if you know your history and you've read the Quran or you've read the Bible, you would know that the world was actually under a great flood. The entire world was flooded. There was this huge flooding, and all land went underwater. That's the story of Noah's Ark, isn't it? Well, that left all around the world all sorts of interesting things. It carved out Gully Ali Beg and other places in Kurdistan. In New Zealand, it actually buried all of these great forests underground because basically these huge waves hit the forest from the coast, and they flattened all of these trees, and then they got buried under the silt. And then thousands of years later, me and my friend Kelvin, we're walking along the farm, and we notice there's this twig sticking out of the ground. And with a little bit of investigation, we discovered there was a giant karri tree underground. That's my friend Kelvin there. And we actually did a little bit of investigation using ground penetrating radar, and we found about 20 of these trees underground. And so we spoke to Kelvin's dad and we said, hey, you know what? These trees are probably worth a lot of money if they haven't rotted. Why don't we dig them out and mill them and dry them out and sell the wood? And Kelvin's dad said, yeah, let's do that. And it was a very big project. We got about 15 of these trees out of the ground. We milled them, and then we dried them out. We built a drying shed on the farm, and we got some investors involved in it because we couldn't afford all the machinery to do this on our own. But basically, we made around $200,000 and we had to share that with the investors, but that's what we did. But these trees were buried underground for thousands of years in a swamp. Why? And they were completely wet. You can see that there. The moisture content was around 300% at the time. Well, how did we, and we had to dry them out in a drying shed, as I said last lecture, for 2.5 years to get the wood to a good strength. Why did it not rot? Well, it's because there was no variation in moisture content. The moisture content was high and it stayed high. If the moisture content was going up and down, we would have had shrinking and swelling and the wood would have broken up. That didn't happen. It stayed high. The water actually protected the wood. And so, yeah, we actually still... I have certain bits of furniture made from that tree itself, and yeah, you can see the wood is perfectly fine. I'll try and show you a box that I have made from that tree, if you like, when we have the Zoom tutorial. But yeah, that's durability. Karri is a very durable material because it's very, very dense. And the fact that it's been buried in a swamp for thousands of years does not actually decay it, because it's all about the variation of moisture content rather than the height of moisture content. So yeah, it's a beautiful wood too. That's a picture of a Karri coffee table. Now that's made from swamp Karri. As I said, you can't cut down a Karri tree, they're protected, but you can dig up these Karri trees that are buried underground. And so that was made from a tree similar to the one you just saw before. It needs to be dried for about 2 years to get all of the moisture out of it. That's another table. Really beautiful wood, isn't it? Look at the marbling and the grain. There isn't a wood quite like it. It looks almost like marble. And this is actually a gift shop in a tourist area in New Zealand, and it's actually got 2 stories, and they've actually made a stairwell to the 2nd story on the inside of a Karri log. So you can see there, that's not plastic, that's not made of concrete, that's actually a real tree trunk, and it's an old swamp Karri, and they've carved out a stairwell through the center of it. And yeah, right there, it's not just used for structural engineering. Increasingly now, Karri, they're making it for ornamental things just because the wood is so attractive. So there's an electric guitar made out of swamp Karri. I've got a couple of other Karri things I can show you in the Zoom tutorial. So now we've talked about durability so far in terms of the types of decay that can happen, and the types of wood that we can get in terms of species of trees, heartwood versus sapwood and so on, and the variation in durability for them. Let's say we have a timber already and it doesn't have particularly good durability, but we want to improve the durability. We want to find a way to stop insects breaking down the wood. We want to find a way to improve its durability. Well, there's a type of treatment we can do where basically we are trying to inject the wood with high-pressured chemicals, and these chemicals will penetrate into the wood just like water would, and it's being squeezed into the wood because it's under high pressure, and that chemical will basically be poison for any insects, and so insects will not want to penetrate into the wood. Now obviously how much the chemicals penetrate into the wood, that depends on the porosity of the wood. And so the chemicals will penetrate into sapwood and softwood more than it will penetrate into heartwood and hardwood, respectively. But that's okay, because sapwoods and softwoods are the woods which they tend to have a tendency to have lower durability because there's less density. And so when you actually inject these chemicals into these woods that would otherwise have low durability, you suddenly give them high durability. But there is a bit of an overlap here. So for an example, untreated oak is more durable than untreated pine. However, treated pine is more durable than untreated oak. So by treating the wood chemically, you basically can make a low quality kind of timber, such as pine, have the same or better durability than an untreated high quality kind of timber like oak. And I will have to say that nearly all timber now that you would buy in the shop would have some kind of chemical treatment. So how does this chemical treatment work? So with the chemical treatment of timber, I've actually put a video of what it looks like on Moodle. But basically what they do is, after the timber has been milled and it's been dried, they will then bundle it together, as you see on the picture on the right, and they will put it into a high pressure vessel. And in that vessel, they're going to actually fill the vessel up with a chemical. This chemical will usually be something with mild acidity, so basically it would kill any bugs or fungi or bacteria. And they pressurize it to not a huge pressure, probably about 2-3 bar, and that squeezes the chemicals into the wood. So you can see that on the left, that picture, you can see a timber. The wood is being penetrated by this chemical by high pressure. Now, a very important thing is that it only ever penetrates onto the surface of the wood. It can't go right to the end, and therefore it creates a protective coating. The bugs are not going to cut through that to get to the unchemicalized wood, but that's okay. The issue comes, however, when you actually cut one of these timbers. You get after it's been treated, you get a saw out and you cut it in half, and then you've got a part of the timber, one of the faces, which is exposed to the atmosphere, and that has not been treated. And then bugs and bacteria and fungi, they can enter the timber and rot it. So that's why when you cut a piece of wood, you've actually got to paint it with a chemical paint called end paint. And in the video that I'm giving you about high pressure chemical treatment, it talks about this. This is a way to make sure that the wood is completely coated in this chemical barrier. So a couple of notes on treatment of wood. I will say that treated timber is so common. Really, nearly all timber, especially if it's being used in building in any sort of capacity, it should be treated to some degree chemically. Well, this is a difficult thing for availability in some parts of the world. Kurdistan doesn't have a lot of trees, and it certainly doesn't have any chemical treatment facilities at timber mills. But a lot of the timber that's being imported from Turkey is treated, or sometimes they say it is treated even though it hasn't been. So you've got to be careful there. And when you cut it, you need to paint the ends with the face that has been cut with an end paint, because that face will not have the chemical treatment, because the log or the lumber or the timber that was put in whole into the chemical treatment tank. Now The other thing is it can affect the colour of the timber. Usually the timbers go in fairly yellow and they come out rather grey in colour. That gradually their colour will go back to normal, but when they first come out, they come out kind of grey. So the picture I'm showing you, that's actually a company called Croft Poles, and what they do is they cut down radiata pine trees, and they basically take the big trunks, treat them, and they sell them to be effectively electricity poles for distribution networks. And one of my friends from university actually started this company, and so he's a very rich man now. He's making these poles, treating them, and they're replacing a lot of the concrete poles that hold up electricity lines around New Zealand now. So a couple of things with treatment. You've got to know that actually what you're using the timber for, that will determine what kind of chemical you use and what class of treatment it is. So the British have come up with a standard called 3351. So BSEN. BS stands for British Standards. I know what you were thinking, Schleidel. And EN is for engineering. So these are typical engineering standards, and they've put different treatments of timber into classes. So class 1, this is if the timber is going to be used inside in a dry environment. 2 is if there's a risk of it wetting. So skirting boards, that's the timber that goes around the edge of the wall and the ground in your house. That's a skirting board. 3C, C stands for coat or coating, and UC stands for uncoated. Okay, so class 3C is if that means the timber can be used outdoors, but it must be painted. If it's 3UC, it doesn't need to be painted. And 4, it means it can have direct contact with soil or fresh water. That means you can potentially use it as a pile to go under a wharf in a pond. You could bury it in the ground as a fence post, and it won't rot. So those are different treatment standards. You need to be aware of that, because when you buy timber as an engineer for a typical engineering project, you need to think, what am I using that timber for? And then you need to consider what class of treatment does it need to get. You don't want to bury class 1 timber into the ground because it'll rot. Likewise, you probably don't want to use class 4 timber as your skirting board, because that's just going to be very expensive. As you go up these classes, class 1 to 4, the chemical being used is more concentrated, and so the expense is higher. So that's a little bit about treatment. Now, we've covered everything there is to know about wood at this stage and timber, but I now want to talk to you about wood products. And what do I mean by wood products? Well, one of the most difficult things about timber is you're kind of limited in the range of sizes and shapes you can get timber in. And you can fix that a little bit with malleability. You can bend timbers and poles a little bit, but you can't do too much with it in terms of shape, because basically the shape of the timber is determined more or less by the shape of the tree, and trees never grow in the shape you want them to. And so basically timber is usually long straight planks or poles, and they're often never much more than maybe 8 meters in length. 8 meter would be a long length timber, usually 2.5 meters. So that's a real big problem, isn't it? With concrete, it's great. You can make concrete into whatever shape you want. Wood, you can't do that. The other big problem is that when you have lumber, you've cut down a tree, and you're trying to millet into timber. What a lot of people don't realize is that 40% of the wood is wasted. That's wood on the outside, sapwood, bark, offcuts, branches. There's a lot of waste. Now, we've got these two problems here, and they can basically be combined to create a solution called wood products. The waste wood from the timber mill yard, that can be turned into various wood products which are different shapes to what you potentially can get with timber. And just like wood, with wood products, durability can be improved with chemical treatment. So what do I mean by wood products? Well, one of the most obvious one, and you weren't thinking of this, is plywood. Plywood is basically very thin sheets of timber called veneers, where basically you put the big lumber through a giant pencil sharpener, which basically cuts the timber into long flat sheets, and then you squeeze these veneers together with a resin in between them, and they're stuck together, and they're usually 3 veneers or to maybe 6 veneers thick, depending on what kind of plywood you need. And then they're dried, and they can be and then you've got plywood. And now, rather than having long planks, which are the shape we can get timber in, we can now have big flat sheets. So suddenly we have a way of using wood in a way to make floors or frames or doorways. And so that's quite a useful thing. Now, when you're actually shaving the wood into a thin veneer in this spiral pattern, it's very important that the wood has good elasticity, a low modulus of elasticity. Otherwise, it will basically crack and break as you're cutting it. And so you need to basically, to get that malleability, you need to have a high moisture content to get the flexibility. And so softwoods such as pine, Douglas fir, birch, they are often used for plywood. Another type of wood would actually be a hardwood such as poplar. That works reasonably well too. But they also need to be very tall and skinny, tall and straight trees in order to be able to make the plywood. Now, that may not make a lot of sense to you. There's a great video, the link is on Moodle, check it out. You can watch how plywood is being made. It's very exciting, you're going to love it. So this is a picture of the different veneers being stuck together. So this is plywood, and you can see that there's 5 veneers there that are going to be stuck together with a glue to form the plywood. And do you notice something? The veneers, the grain of the wood goes in opposite directions. Why is that? Well, it's because when the veneer was cut, it had very high moisture content. As it dries, it's going to actually shrink, and if you've got all of the grain going in one direction, then the plywood is going to twist and bend. But if they're in opposite directions, that keeps the plywood nice and flat. You're going to see this when you watch the video of plywood being made, how the grains for each veneer are perpendicular to the one above. So a couple of properties of plywood: they're very flexible. The modulus of elasticity is much lower than for timber, and the reason for that is there's actually a little bit of flex in the resin itself between the veneers of wood. And but the great advantage of plywood is that it's got this flat shape. That's really useful. You can use it for making walls or for floors, I've actually built a boat using plywood before, so it's a great material because it's a very useful shape, which is not what you can say for a lot of timber. Now, what you need to remember though is that plywood, it's very low strength, and that's because the glue is not particularly strong, and the veneers, when you're actually moving them around and you've got them in opposite directions with the grain, then only half the grain are going to be in the direction of the load. So half the grain will be perpendicular to the loading, half will be parallel, and that halving reduces the strength of plywood. Plywood is not particularly strong, and because of that, you've got to be careful where you use plywood. You can't use it for a lot of structural loading. If there's very high structural loads, then plywood is not suitable. Because it's a low strength, not only in tensile but also flexural and compressive strength. Now, it has a very high absorption capacity. Why is that? Well, it's because you're actually cutting the wood into very thin veneers. You're actually creating a lot of surface area. Now that means if the plywood is exposed to damp conditions, and there can be that variability of moisture content. So on a wet day, the moisture content goes up. On a dry day, it goes down. Well, that's going to cause the plywood to warp and distort. So you can see there a picture of a piece of plywood on a wall of a shed, how it's all distorted and warped out of shape. That's because water is getting into the plywood. Another term for this warping or distorting is a word called creep. It's different to the creep that we referred to when we talked about concrete, but it's basically about how the material will change shape under with moisture content. So that's a problem with plywood. Now, I want to talk to you about another kind of wood product. This is particle board. As I said, there is a lot of wood waste when you're milling timber from lumber. And if you ever go to a timber mill, I hope you do get a chance at one point, you're going to see that there's sawdust and bits of waste wood all over the place. Now, with all that waste wood, you can actually gather it up, chip it up and make it all one size, soak it in a glue and adhesive, and compress it into a flat board. Now this is called particle board because you're using particles of wood, sticking them together. Now, what do you think about that? Does it sound like a good idea? Yeah, it works pretty well. A couple of things. First off, it's very cheap. It's a lot cheaper than plywood. Plywood is a bit more expensive, but particle board, because you're not having to cut the wood into little resins, veneers, and because you're essentially using the waste from a timber mill, it actually is very cheap. But it does have some downsides. Look at that particle board there. You can see it has lots of little holes all through it. Water is going to penetrate into that very easily. It's got very high porosity, a very high absorption capacity. Now, particle board can vary on the size of particles. So sometimes you have very fine particle size, where basically it's just very refined sawdust. And sometimes the particle size is very large. They're big wood chips. But either way, they're stuck together in particle board. So you can see here two different sizes of wood chips. So normally you would sort this out with a sieve or a wood chipper, but you can see the particle board on the left. That's using wood chips, which has an average of 5 centimeters in length. And the particle board on the right has an average particle size of 5 millimeters in length. And so it looks a bit different, doesn't it? Like you can see all the individual grains of the particles in the 5 centimeter particle board. What you need to know is that the smaller the particle size, the weaker the particle board. Also, generally, the cheaper the particle board too. But yeah, even it's very inflexible. The reason is that if you try to flex it, it's going to break in the resin. So remember, plywood had good flexibility to it. Particle board does not. It does give you a nice good flat shape, which is good. Low strength, and I mean considerably lower than plywood. And the other big issue is a high absorption capacity. So if you're using particle board in anything, make sure it's in a place where it's not being exposed to water. So that picture you see on the right, that was actually a house in Oman, and the idiot who built this house, he actually put a particle board in as the floorboard for the bathroom. So basically every time someone got out of the bath and toweled themselves off, water would go onto the floor and it would slowly penetrate into the particle board, and that's why it's destroyed there. It also has a very low elasticity. So unlike plywood, which can have reasonably good elasticity, particle board has very low elasticity. So there's a few properties of particle board. Well guys, that's enough for wood and wood products. I hope you've enjoyed this series on wood. This is not homework, this is supplementary reading. Everything you need to know is covered in these lectures and in the videos that are on Moodle, so check those out. But this should give you everything you need to know to do assignment 6. Now guys, if you do want to do supplementary reading, just go to this book, Shan Somayaji's Civil Engineering Materials, and read those pages. Those are the pages that are particular for wood and wood products, to the depth that I use those pages when preparing these lectures. So guys, I hope that was helpful for you. I hope you enjoyed it, and if you've got any questions, give me a phone call or an email, or I'll speak to you on Thursday when we have our Zoom tutorial. Thank you and goodbye.